Good morning everyone and welcome to our ISO programming and CNC turning course. Today we begin to see how the lathe moves within its space. Of course we know that it moves via codes and commands given by a CNC. Let's open this first diagram and try to understand something. The space inside the machine is seen according to two Cartesian axes that are nothing more than two intersecting straight lines, one horizontal and one vertical. The point of intersection is 0. Moving to the right on Z will go from 0 to plus, therefore 1, 2, 3, 4, and so on. Moving to the left towards the chuck will go from 0 or minus, that is minus 1, minus 2, minus 3, minus 4, minus 5, etc. The axis perpendicular to Z and X and determines our diametrical position. Moving towards the tool, usually on modern machines it is upwards, on older machines it was towards the operator. It doesn't matter, once we understand how the machine moves, moving towards the tool we go from 0 to plus, i.e. x1, x2, x3, x4, moving from 0 away from the tool we go minus 1, minus 2, dash 3, dash 4. Normally we work in zeta minus x plus. One thing that must be said about x is that x is diametrical. Therefore a movement from x0 to x50 generates a turning operation, yes, a 50 mm diameter, but a physical movement of the tool of only 25 mm. Therefore automatically we at x go to the diameters. When we mount a tool in the turret, the tool does not know where it is in relation to the workpiece, in relation to the machine. It knows absolutely nothing, so with a process that we will then see, with the software that we will use later, once the tool is mounted on the machine we will have to go against the face of the workpiece, tell it Z0 measure, that's your Z0, turn a diameter. Let's assume we have supplied a diameter, have turned it and measured it to 100 and told the CNC, at which point your position will always be known to the machine. Normally the workpiece 0 is done 2 or 3 mm inside the workpiece, so that 2-3 mm of blank will be removed to have a complete machining. Normally these are workpieces that are either rough in crust or cut with a hacksaw, so it is advisable to machine them right to the center. Having said this, we can start to see the programming, so let's mount the workpiece on the machine, establish what we have to do, mount a tool suitable for that machining, after which we go to 0, i.e. to tell it its position with respect to the 0 point. How? We'll see later. Now all we need to know is that physically we have to go and get a tool suitable for our machining. In this case I want to turn cylindrical. I'll never go and mount such a tool. Why? Because I will be able to turn cylindrical, but not facet, so I'm going to mount a tool that allows me to work in both directions. In this case I'm going to choose a CNMG, i.e. a rhombic 80 degrees, radius of tip 0.4 and rolled a 12 mm diameter. What also matters when I'm going to mount a tool, the protrusion. The tool must always protrude as little as possible, taking into account the overall dimensions of the machine, so I will always make it protrude as little as possible. The more it protrudes, the more I run into possible vibrations. If it is a boring bar, I will have measurements that are not constant over time machining. With a roughness that is too high compared to that required, let's make it protrude as little as possible. Well, here we are inside our programming editor. Currently we have only one tool mounted, and we have on the machine a workpiece diameter 100, which we are going to one face and turn on the outside diameter. So first of all, let's establish with what tool we are going to face it. We only have one. It is not difficult. T01M6. Some machines, especially the Fanuc and the more modern ones, to cool the turret and make it rotate simply need a code T0101. Italian machines such as ECS T01, M6 and T01 can be the name of the turret, but also the name of the corrector that is associated with the turret. A little more complex. Sincerely, the Japanese were a little faster. This software is based on Italian-type programming. Then it will be necessary to rotate the spindle. M3 makes the spindle rotate, then the M4 rotates the spindle, then the self-centering. The difference between M3 and M4 is simply the direction of rotation. In this case we will use M3. If we used M4 we would have to turn the tool backwards. Very simple. G97 or G96 establish what? The S establishes the number of revolutions or the constant cutting speed. G97 makes S800 be 800 RPM of the auto center or of the spindle, regardless of which diameter I'm going to turn. G96 S800 on the other hand would indicate constant cutting speed, i.e. depending on the diameter at which I'm working, the machine increases or decreases the revolutions, causing 800 meters of material to be developed on the tip of the tool every minute that passes. Absurdly, X0 would correspond to infinite revolutions, which is why there is normally a code, which in this case is not contemplated. On the Fanuc it is G92S2000, which ensures that the auto center or spindle can never exceed 2000 RPM, regardless of the programmed cutting speed. G95 always better to put it. Normally the machine starts already in G95, but it's not guaranteed, so let's put it because we don't know who has worked before us on the same machine. If he used G94 then we are in millimeter per minute, that is, even with the chuck stopped in working conditions we can advance the tool. G95 instead works millimeter per revolution, so we can only work when the chuck rotates. Well, let's get closer to the piece. How do we do it? We do it in rapid traverse. G0 tells the machine that all the coordinates that I'm going to enter will be reached in rapid traverse. We have said that our external diameter is 50 millimeters, that of the blank, so we'll go to X55.0 Z0.0. What does it mean? It means that I'll go to a safety distance, that is 5 millimeters from my blank, to AZ at which I can start working because I'll want to cut at 0. Well, let's start working then. G, 1 rapid movement X0, or even better X minus. Let's do X0. I don't want to confuse you. X0.0 F0.3. What's this F0.3? Well, it's the feed rate expressed in millimeters per revolution. As the tool moves towards the center of the workpiece, each revolution of the chuck will move the tool. It will be 3/10 per revolution. F0.3. I've checked time in the center of the workpiece. I'll have to peel off G0 Z1. I want to peel off diameter 45 for a length of 40 millimeters, so always X45. At this point in G1Z 40.0, what F should I use? If I don't repeat it, I'll use the F used at block number 005. By block I mean command line N002, a block N03, another block, so on. If I want to go a little harder or slower, F0.5. Having finished my machining in rapid G0x150.00 at 50.0, I detach myself from the workpiece and write M30, and M saying, well, you've finished, rewind, we'll start a new workpiece. I run it and see if it gives us any error. It gives us no error. The spindle rotates, my approach is quick, and I go to X0 to work. I detach myself by 1 mm. I go to X45 and work in Z effect in and a typing error. Big problems. Let's see what happens. The beauty of having a virtual machine is this. If we were on a normal machine, my legs would be shaking. Crush. There you go. Okay, so always reread the programs after you've done them. There's something that's not nice about this program. It's sharp-edged, so we've been programming. In work one coordinate at a time, but if we go up a little less after turning in our workpiece. In G1 we go to lean on the workpiece itself, 3, and before cylindrical turning always in G1. We don't have to repeat G1 and I repeat it so we have greater clarity. We put X45 and Z 2.5. By doing so we in a block with G1. And are going to enter 2 coordinates. The reaching from X40 to Z0 of the 2 coordinates will be done according to a straight line, okay, so if we need an inclined angle 30 degrees or 45 degrees we'll put different coordinates. Direct programming will help us, but we'll see that later, what happens. Perfect. With our MS we can also manage other things of the machine. We put an M8 and an M9. We run the program. What does M8 do? All it does is activate the coolant. M9 will switch it off. 4. When we buy a machine we are given a list of MS, a list of GS. The GS are fairly standard. The MS can be customized, so you have to close a door because you have pneumatic doors. There'll be an N. You need to open and close the spindle. There'll be an N. You have to learn those by heart. Normally it's a good thing to put this list on the machine if you're going to do programming on the machine. Well, I'd say that we're done for now. Try to reread some of our codes. Take a square sheet of paper, mark the z-axis, the x-axis used in squares with units, and make some small programs where I started to move in Cartesian axis space. Remember, the z is normally programmed in negative, the x in positive. I apologize if I sometimes make mistakes. I know I'm not a good YouTuber. The habit of often saying self-centering or spindle and making a bit of confusion comes to me from the many years spent on the machine. It's a mistake. Forgive me those small errors of expression, due to the fact that I wasn't born a teacher anyway, but mainly a mechanic. I thank you for your attention, and I hope I've been useful, at least a little. Thanks to all. Good day.